Steam boilers did not simply fail, they came apart with the violence of buried artillery, turning quiet boiler rooms into fields of wreckage. In the early factories and riverboats of the 19th century, men worked only a few feet from iron tanks that held more force than they understood. Pressure gathered in silence, metal weakened without warning, and a single misjudgment could rip an entire building apart. Survivors spoke of walls lifting, floors trembling, and a blast so sudden the human mind could not react. So what made these machines fail with such devastating finality? If stories like this move you, consider subscribing to our channel to help preserve the forgotten history of those who built our world. Now let's see about the hidden physics inside steam itself, and the men who learned its dangers the hard way. Steam power arrived like a promise. It turned small workshops into factories and slow riverboats into engines of commerce. But behind the confidence of the 19th century stood a machine almost no one fully trusted. The early steam boiler was simple in appearance, just a metal shell filled with water and a fire beneath it. To the men who fired them, they felt solid, permanent, and heavy enough to be reliable. Yet the truth was that these machines were always waiting for a moment of weakness. The boiler was a vessel designed to hold pressure, but that pressure changed constantly. As demand increased, the firemen fed the furnace harder, and the water climbed toward a boil that was supposed to be predictable. In theory, gauges and valves kept things stable. In practice, the early decades of steam engineering were still a long experiment. No one knew exactly how strong a boiler stayed after years of work. They simply hoped the metal remembered its shape. Factories depended on these machines. Steam drove sawmills, textile plants, printing presses, and ironworks. The sound of pistons and the hiss of valves became part of daily life. Men walked past boilers without thinking twice, even though each one held energy capable of flattening a building. Workers trusted what they understood, and most had grown up around fire and iron. But steam was different. It was invisible until it escaped, and the pressure inside a boiler behaved in ways even skilled hands could misjudge. The internal forces were immense. Pressure does not rise like temperature, slow and steady. It can spike in minutes with the right combination of heat and water levels. A stuck valve or a sudden demand for more power could push a boiler past its limits before anyone noticed. The line between safe operation and catastrophe was thinner than industry wanted to admit. Early engineers assumed thicker iron meant greater safety. The problem was that iron itself was inconsistent. Castings varied from foundry to foundry. Some plates were riddled with imperfections that only revealed themselves during failure. Rivet holes created stress points, seams expanded and contracted with every cycle of heating and cooling. A boiler aged from the inside out, its most dangerous weaknesses hidden where no one could see them. This created a false sense of security. If a boiler looked fine on the outside, many assumed it was fine within. Accidents began early and never truly stopped. The 1830s and 1840s were filled with reports of riverboats tearing apart mid-voyage, mills collapsing, and workshops shattered by explosions described as instantaneous. A boiler did not merely break, it tore open with explosive force, sending shrapnel through brick and timber. Investigators often found no clear warning sign. The aftermath left only fragments of metal curled back like paper. These machines built the modern world, but they did so at a cost. Every community had stories of a boiler that failed without mercy. Beneath the progress of steam lay a truth no one liked to confront. The power that lifted industry upward was the same power that could bring it crashing down. To understand why so many boilers failed, you have to look inside the system long before the metal ever cracked. Steam pressure was not just a measurement on a gauge, it was a force that behaved according to rules most 19th century operators had never been taught. Many firemen came from backgrounds in carpentry, farming, or general labour. They learned boilers the same way they learned every trade, by watching the man before them. What they did not receive was a foundation in thermodynamics, a field still being defined as these machines roared to life. The problem was that steam could change state faster than human intuition could keep up. Water heated in a confined space expands with extraordinary speed, and when the temperature reaches certain thresholds, small increases in heat can trigger massive increases in pressure. This was the part few operators grasped. A furnace stoked a little too aggressively, a water level allowed to drift slightly too low, or a draft change beneath the firebox could transform a stable boiler into a volatile one in moments. Gauges added a layer of confidence, but early pressure gauges were notoriously unreliable. The Bourdon gauge, introduced in the mid-1800s, made readings more precise, yet even it suffered from vibration, wear and calibration issues. In factories where dust and grit filled the air, sensitive instruments degraded quickly. Some gauges stuck, others lagged behind real conditions, and many were never checked after installation. For men in boiler rooms, a reading could be reassuring right up until the moment it became irrelevant. Steam engines attached to these boilers also influenced pressure in ways that were poorly understood. Sudden load changes, such as a machine engaging or disengaging, created instant fluctuations inside the boiler. If a large piece of equipment stopped suddenly, the steam no longer being used surged back into the system. This spike could overwhelm the boiler faster than a fireman could react. The relationship between mechanical load and internal pressure was a delicate one, and industrial schedules often pushed equipment to operate at the edge of that balance. Ventilation played a part as well. Furnace drafts were controlled through dampers, but these were often crude sliding plates or chains that workers adjusted by instinct. A gust of wind entering through a factory door or a shift in outdoor weather conditions could alter the airflow beneath the firebox, increasing the heat in ways no one expected. In winter, when doors stayed shut, the draft could drop suddenly and then surge again when opened. These daily fluctuations were enough to turn routine operation into dangerous territory. Even water itself could become a threat. Minerals in feed water created scale on boiler surfaces, forming an insulating layer that slowed heat transfer. This made firemen compensate with hotter fires, unaware that the metal beneath the scale was heating unevenly. When the scale eventually cracked or flaked off, superheated metal suddenly touched cooler water, producing violent, instantaneous steam flashes. The pressure spike from that reaction had destroyed more than 1 mil without warning. Pressure rises were not gradual stories, they were moments, brief and unforgiving. Men talked of hearing a quick change in the boiler's voice, a sharper hiss or a deeper rumble, but these signs came only seconds before disaster. By the time the danger was visible, the physics had already taken control. Long before a boiler burst, its metal had already begun the slow process of surrender. Every heating cycle stretched the iron plates, and every cooling cycle pulled them tight again. This endless expansion and contraction created stresses no one could see. In the 19th century, the concept of metal fatigue was barely understood, and most builders assumed that if a plate looked intact, it was strong. The truth was far more complicated. Boilers aged from within, and the signs of their weakening could remain invisible until the final catastrophic moment. Iron from that era varied wildly in quality. Many plates were rolled in mills that lacked modern controls, producing metal with uneven density and hidden slag inclusions. These flaws were harmless under low pressure, but fatal under repeated strain. Over time, microcracks formed along these imperfections. They started as threads thinner than a human hair, yet each cycle of heat widened them. Eventually the crack travelled across a plate like a fault line waiting for release. By the time anyone noticed, the damage was already permanent. Riveted construction added its own vulnerabilities. Boilers were assembled from curved plates joined by rows of rivets, each hole drilled or punched through the metal. These holes created natural stress concentrations. As steam pressure pulsed inside the vessel, the edges of every rivet hole flexed. After years of service, these small movements loosened the rivets and elongated the holes. A row of failing rivets could unzip a boiler seam in seconds, releasing steam with explosive force. Riveted joints were only as strong as their most weakened point, and often that weakness remained hidden beneath layers of insulation. Internal corrosion posed another threat. Water used in boilers was rarely pure, and impurities reacted with the iron to create rust. This corrosion tended to form in pockets where sediment settled, especially at the bottom of the boiler where circulation was weakest. The rust ate through the metal from the inside, thinning it unevenly. A plate might measure a safe thickness in one spot, yet be dangerously thin only inches away. Inspectors of the time lacked tools to detect this kind of localized damage. Many boilers that appeared sound were already compromised beyond recovery. Stays and braces, the internal supports that kept boiler walls from bulging outward, also fatigued with age. These rods endured constant pressure that bent and flexed them ever so slightly. If a stay yielded or snapped, the wall it supported could bow outward. This deformation increased stress on neighbouring plates, creating a chain reaction of structural failure. Some explosions were later traced to a single stay that had reached its limit without leaving any visible warning. The environment of the boiler room accelerated this decline. High humidity, constant vibration, and extreme temperature swings wore down the structure faster than builders predicted. The men who worked near these machines often spoke of hearing a faint ticking or groaning as the boiler expanded. These sounds were not warnings, only the natural music of metal under strain, but they masked the deeper noise, the microscopic tearing that grew with every cycle. Metal fatigue was a silent enemy. It did not announce itself with leaks, cracks, or discoloration. It accumulated quietly over years of service until the day the boiler reached a point from which it could not recover. When the failure came, it was sudden, total, and irreversible. The iron that had faithfully held steam for decades gave way in an instant, leaving nothing behind but shards and questions. The boiler room was often the most overlooked space in an entire industrial complex. It sat beneath workshops, behind mills, or below the decks of riverboats, out of sight and far from the attention of managers. To outsiders, it was simply the place that made steam. To the men who worked inside it, the room felt like a world apart, hotter, darker, and more unpredictable than any other corner of the factory. This isolation created a culture in which danger grew quietly, shielded by walls that few people bothered to enter. Many early industrial buildings were not designed with safety in mind. Boiler rooms were squeezed into leftover spaces, basements or makeshift annexes added long after the main structure was built. Their low ceilings trapped heat. Their brick walls absorbed vibration. Ventilation was often an afterthought, leaving the air stagnant and thick with moisture. Thermometers fogged, gauges sweated, and the smell of damp iron mixed with coal smoke in a way that made every surface feel alive. In these conditions, even routine tasks required constant adjustment. The firemen who tended these boilers worked under enormous physical strain. Temperatures regularly climbed past levels that modern safety standards would consider extreme. Sweat ran into their eyes. Clothing stuck to their skin, coal dust settled in the folds of their sleeves. Shoveling fuel into the furnace became a rhythmic battle, each motion feeding the machinery that powered the entire building. With every shovel load, the fireman had to read the behaviour of the flame, the draft in the flue, and the slight changes in the boiler's tone. These were skills learned through experience, not instruction. Because the boiler room was out of the public eye, conditions often slipped below acceptable standards. Leaks were patched with makeshift solutions. Valves were cleaned only when they became a problem. Insulation fell away from piping and was never replaced. Managers focused on production deadlines rarely descended the stairs to see the state of the machinery. Their understanding of the room's needs came second-hand, filtered through workers who worried more about keeping the plant running than asking for repairs. This gap between oversight and reality widened every year. Lighting was poor in many boiler rooms. Lanterns cast flickering circles on walls coated with soot, making it easy to miss signs of trouble. Dampers and control rods corroded in the shadows. Rust formed unnoticed on brackets and flanges. Steam seeped from joints and disappeared into humid air before it could be traced to its source. In this dim environment, men relied on touch and sound as much as sight. A loose bolt or vibrating pipe might be detected by feel long before it was visible. Noise added another layer of difficulty. The constant roar of the furnace, the rumble of engines overhead, and the rhythmic pulse of pumps created an environment where subtle warnings were easily lost. A shifting plate or straining stay sounded no different from the routine groans of machinery. Even if a worker sensed something wrong, communicating that concern up the chain was not always easy. Boilermen often carried the reputation of being overly cautious or prone to worry. Their warnings were not always taken seriously. This physical and cultural isolation made the boiler room a blind spot in industry. It was a place where machines aged without supervision, where hazards accumulated unnoticed, and where the people most familiar with the equipment had the least influence. When a failure finally came, it was not just a mechanical event. It was the result of years spent in the shadows, out of sight and out of mind. The instant a boiler fails is not a gradual unravelling but a violent negotiation between pressure and structure. Inside every vessel, steam is always searching for release. As the temperature climbs, the molecules strike the walls with increasing force, testing every seam, every rivet, every plate. Most days the boiler holds, but when the internal force finally exceeds the strength of one weak point, the reaction is immediate. There is no hesitation, only the sudden triumph of pressure over iron. That weak point could be anywhere. Sometimes it was a plate thinned by unseen corrosion. Other times it was a rivet row stretched to its limit after years of strain. Even a small defect, no wider than the edge of a coin, could determine the fate of the entire structure. Once pressure found this vulnerable spot, the crack expanded with tremendous speed. Metal does not tear slowly under steam load. It ruptures in a single catastrophic motion. The first sign of failure described by survivors was often sound. Not a roar, but a sharp report like a cannon fired in the confined space. This was the plate yielding. The force inside expelled the weakened metal outward, creating an opening that widened instantly. Steam poured through the breach with violent acceleration, escaping at speeds measured in hundreds of miles per hour. In that moment, the boiler ceased being a vessel and became a weapon. The rupture did not remain localized. As steam escaped, the pressure in the intact sections of the boiler shifted abruptly. This imbalance placed enormous stress on neighboring plates and seams. A failure in one quadrant often triggered additional failures moments later. Investigators examining the remains of explosions frequently found the boiler torn into multiple pieces, each fragment hurled in a different direction by the sudden release of stored energy. In factories, the expanding steam stunned entire rooms. Workers reported being thrown off their feet, blinded by white vapour and deafened by the concussion. In riverboats, the impact could tear through decks and send machinery flying into the air. Timber beams snapped. Brick walls folded outward. Even heavy machinery anchored to the floor was sometimes dislodged and thrown across the room. The violence was not merely destructive, it was transformative, turning solid materials into debris scattered over astonishing distances. The physics behind this force is rooted in the amount of energy contained within superheated water. When water exists under pressure at high temperatures, it holds far more energy than boiling water at atmospheric conditions. Once pressure is lost, the superheated water flashes into steam instantly, expanding with explosive power. This flash, known to modern engineers as a rapid phase transition, was poorly understood during the age of steam. To the men who witnessed it, it felt like fire erupting from water. The aftermath always told a consistent story. Plates were curled backward, rivets were sheared clean, and fragments of the boiler lay embedded in walls or roofs. From these clues, investigators learned to trace the origin point, the place where pressure found its opportunity. Every explosion revealed a moment in which the internal force overwhelmed the final barrier. The rest unfolded in fractions of a second. What made these moments so deadly was not just the power of steam, but the speed at which events unfolded. A boiler could appear stable right up to the instant of failure. There was no countdown, no build-up that could be seen or heard. When the weakest point finally surrendered, the entire story was over almost immediately. The most troubling part of boiler failures is how often warning signs were present long before the final rupture. These clues were subtle, inconsistent, and easy to overlook in the daily noise of industrial life. In the 19th and early 20th centuries, boilers did not come with diagnostic systems, monitoring sensors, or automated alarms. They relied entirely on human senses, and human senses were not built to read the behaviour of steam. As a result, danger often lived in plain sight, unrecognised until it was too late. One of the earliest signs of trouble was uneven heating. When a boiler heated more rapidly on one side than another, the plates expanded at different rates. This created internal stress patterns that could eventually lead to failure. But firemen rarely saw the exterior of the boiler change shape. Instead, they might notice a faint rhythmic ticking or an unusual vibration in the floor. These cues were so minor, so easily dismissed, that they rarely triggered concern. Industrial spaces were filled with noises. One more was just part of the background. Water level fluctuations offered another clue. Boiler sight glasses were narrow tubes meant to show the height of the water inside. If the water bounced or dropped unexpectedly, it could indicate a steam pocket forming or circulation issues deep within the vessel. But sight glasses were prone to fouling. Minerals collected on the glass, making readings cloudy. Some operators tapped the tubes to dislodge buildup, unaware that the erratic movement of the water meant something far more serious. A momentary dip in the column might be the only warning before the boiler experienced a sudden and dangerous spike in internal pressure. Relief valves designed to open when pressure exceeded safe limits were supposed to act as the boiler's final safeguard. In reality, they offered their own subtle warnings. A valve that lifted momentarily and reseated itself with a sharp hiss was telling operators that pressure was reaching the edge of safe operation. But workers accustomed to older machinery grew familiar with these sounds and treated them as routine. When a valve lifted too frequently, some even tightened it down to stop the noise, unknowingly removing the one component capable of preventing a catastrophic event. Another overlooked sign came from the fire itself. In coal-fired boilers, the colour and movement of the flame revealed conditions inside the combustion chamber. A fire burning too bright or surging unpredictably indicated draft problems, or an imbalance in heat distribution. Yet many firemen were never trained to read these details. Their focus was on keeping machinery running, not analysing combustion behaviour. A flame that flickered harder than usual might mean a boiler plate was warping under extreme stress, but to the men at the furnace door, it was simply another moment in a long shift. Even leaks, perhaps the most obvious warning, did not always raise immediate concern. Steam escaping from joints or connections was so common that many workers accepted it as part of daily operation. A small jet of vapour might hiss from a flange for months without incident. Only when the leak worsened or the sound changed did anyone consider shutting down the system. By then, the internal damage was often well advanced. The danger was not that signs were absent, but that they were faint, inconsistent, and easy to misinterpret. In the age of steam, a boiler gave hints of its condition, but it spoke in a language most men were not taught to understand. When those hints went unnoticed, the path to failure was already set. Relief valves were meant to stand between a working boiler and a catastrophic failure, yet they were among the most misunderstood components in early steam systems. These valves were simple in principle, a calibrated mechanism designed to lift when pressure exceeded a safe threshold. But in the 19th and early 20th centuries, the reliability of relief valves depended on craftsmanship, maintenance, and environmental conditions that were far from consistent. For many boilers, the valve was not just a safeguard, it was the only defence left when everything else had gone wrong. The earliest relief valves were crude devices, little more than weighted levers placed over an opening. Their function relied on the precise balance between the force of the steam below and the weight or spring force applied above. As long as that balance held, the valve stayed shut. When steam pressure surpassed the designated level, it forced the valve upward and vented excess pressure into the atmosphere. In theory, this simple mechanism should have prevented countless accidents. In practice, it was vulnerable to nearly every hazard present in a boiler room. Dust and soot were constant enemies. Coal-fired boilers produced fine particles that settled on every surface, including the delicate moving parts of relief valves. When enough residue accumulated beneath a valve seat, it prevented the valve from closing fully. Operators sometimes noticed a faint plume of steam escaping from the valve and attempted to stop it by tightening the mechanism. This short-term solution created a new problem. By increasing the tension on the valve, they unknowingly raised the pressure threshold far above safe limits. A valve meant to open at one point might now refuse to lift until the boiler entered dangerous territory. Corrosion affected valves just as it did boiler plates. Moisture in the air and impurities in the steam created rust on hinges, springs, and seating surfaces. A corroded spring lost elasticity. A rusted hinge resisted movement. In cold weather, valves could even freeze in place. Many failures were later traced to valves that had not opened in years, not because the boiler never approached its limit, but because the mechanism had silently seized. Operators often discovered the problem only after an explosion made the damage impossible to ignore. Tampering added another layer of risk. Some plant owners viewed relief valves as a nuisance. When they lifted, they released valuable steam, reducing the available power for machinery. In a competitive industrial environment, production was everything. There were documented cases of valves being pinned, weighted, or chained to prevent them from opening. Inspectors occasionally found makeshift modifications, such as metal straps or bolts added by workers under pressure to maintain output. These alterations transformed the valve from a safety device into a point of failure. Calibration was another overlooked challenge. A relief valve needed to be set with precision, but few facilities had the tools or expertise to perform accurate adjustments. Valves were sometimes calibrated by guesswork or based on previous settings with no verification. Springs weakened with age. Threads wore down. The intended pressure tolerance drifted over time. A valve that once offered reliable protection could become dangerously unpredictable after years of neglect. When a relief valve finally did open correctly, it was often described as a violent, startling event. Steam blasted into the air with a roar that echoed through that building. Workers felt the vibration through the floor. The sudden release was frightening, but it meant the system had a chance to stabilize. Yet if the valve failed to lift at the critical moment, the boiler was left without any pressure outlet. In that instant, the entire vessel became a sealed container of rising force. Relief valves were the final barrier between controlled power and uncontrolled destruction. When they functioned, disaster could be averted. When they failed, nothing else stood in the way. When a boiler failed, the scale of destruction often defied belief. Boilers were heavy machines, built from thick iron and weighing several tons, yet an explosion could launch them through brick walls or send them soaring into the air like artillery shells. These events were not localized bursts, but sweeping blasts that reshaped entire buildings in a matter of seconds. Factories, mills, locomotives, and riverboats all left behind grim records of what a sudden release of steam energy could do. Investigators studying the remains of destroyed buildings found patterns that became disturbingly familiar. Walls were pushed outward, floors collapsed, and beams were lifted as if struck from below. This upward force revealed a crucial detail about boiler explosions. When a ruptured vessel released its pressure downward, the jet of escaping steam acted like a rocket engine, driving the remaining mass upward with incredible velocity. Some boilers were found hundreds of feet from their original position, embedded in fields or resting atop nearby rooftops. Their flight path showed the energy unleashed in mere fractions of a second. The blast wave created by escaping steam travelled faster than human reactions. It expanded outward through workshops crowded with machinery and workers. Tools, belts, and gears became airborne. Windows imploded, sending glass across rooms in glittering arcs. Even sturdy wooden beams shattered under the expanding force. Survivors often describe the sensation not as heat, but as a violent displacement of air, like being hit by a sudden wind powerful enough to lift them off their feet. Riverboat explosions were particularly devastating. Boilers mounted on decks or between cabins had no solid walls to contain the blast. When one failed, the superstructure of the vessel offered little resistance. The force tore through wooden planks, snapped masts, and threw passengers into the water. Some explosions ignited fires that consumed the boat within minutes. The Mississippi River became notorious for these tragedies, with vessels like the Sultana and the Pennsylvania leaving behind scenes of chaos that unfolded without warning. In factories, the destruction often extended far beyond the boiler room. Explosions could ignite coal dust, wood shavings, or oil residues, turning the initial blast into a chain reaction of smaller fires and secondary detonations. In textile mills, lint floating in the air ignited in bright flashes. In sawmills, resin-soaked timber burned rapidly once exposed to intense heat. The initial failure of the boiler became only the beginning of a much larger catastrophe. The shockwave fractured surrounding machinery in unpredictable ways. Cast iron gears cracked. Drive shafts bent or snapped. Overhead line shafts spinning at high speed were thrown off their bearings and whipped across workrooms like metal flails. These secondary failures were responsible for many injuries, as workers struck by flying equipment often had no idea where the danger originated. Buildings struck by boiler explosions rarely survived intact. Roofs lifted from their frames, brickwork fractured along mortar lines. Doors were ripped from hinges and found far from their original locations. Insurance investigators studying these sites concluded that no material available at the time could reliably contain the force of a boiler failure. Even reinforced walls crumbled when the internal pressure of superheated steam was unleashed. The violence of these explosions left communities shaken. Newspapers ran illustrations of mangled structures and fragments of boilers lying among the debris. Each event served as a stark reminder that steam, for all its usefulness, carried a destructive potential that rivaled gunpowder. The men who worked in these environments knew the risks, but seeing the aftermath firsthand was something altogether different. It revealed the true magnitude of the energy they lived with every day. For decades, boiler explosions were treated as unfortunate accidents rather than preventable failures. Factories rebuilt, riverboats were repaired, and railroads replaced locomotives without fundamentally changing the conditions that allowed these disasters to occur. The idea that government oversight might be necessary was controversial in an age that valued industrial freedom above all else. Owners feared interference, engineers distrusted outside authority, and politicians hesitated to interfere with the engines of national growth. By the time meaningful regulation began to take shape, the death toll had already reached staggering numbers. The first major push for oversight came in the mid-19th century, driven not by industry but by public outrage. Newspapers routinely printed harrowing accounts of riverboat explosions, mill disasters, and shattered workshops. The images of twisted boilers and collapsed buildings appeared alongside lists of the dead, many of them workers whose names were known in their communities. Public sentiment began to shift. People questioned how such powerful machines could be left without standardized inspection or enforceable guidelines. England took early steps, forming inspection committees and issuing recommendations, but compliance was often voluntary. Many owners resisted, citing cost, inconvenience, or confidence in their own practices. In the United States, the situation was even more fragmented. Individual states attempted to pass laws requiring inspections, yet enforcement was inconsistent. Without national standards, a boiler considered dangerous in one state could be relocated and operated freely in another. This patchwork of rules created opportunities for neglect to persist. The turning point came after a series of high-profile disasters that captured national attention. One of the most influential was the explosion aboard the steamboat Sultana in 1865, which killed more than 1,000 people, making it one of the deadliest maritime disasters in American history. Investigations revealed corroded boilers, inadequate repairs, and ignored warning signs. The scale of the tragedy made it impossible to dismiss the need for systemic change. Outrage forced lawmakers to confront the fact that unregulated steam industry posed a threat far beyond the workplace. In response, governments began establishing dedicated regulatory bodies. The United States created more formal overseers for steamboat inspections, and by the late 19th century, organizations like the American Society of Mechanical Engineers emerged to develop technical standards for boiler design and maintenance. These early codes introduced uniform manufacturing requirements, established safety margins, and recommended routine inspection procedures. They represented a shift from reliance on operator judgment to a framework grounded in engineering principles. Still, adoption of these standards was not immediate. Many factories operated outdated boilers long after new regulations were introduced. Inspectors encountered resistance from owners who viewed safety rules as an unnecessary burden. Some businesses argued that downtime for inspections would hurt productivity. Others simply lacked the resources to replace worn equipment. The tension between safety and profit slowed the impact of reform, allowing dangerous conditions to persist well into the 20th century. Gradually, however, the evidence became impossible to ignore. Statistics showed that regions with enforced regulations experienced dramatic declines in boiler-related accidents. Engineers embraced the new codes, recognizing that standardized design and testing improved reliability. Insurance companies began requiring compliance as a condition of coverage, creating financial incentives for safety. Bit by bit, the culture surrounding boilers changed. What had once been seen as an unavoidable risk became recognized as a preventable hazard. Yet even with these improvements, the question lingered. Had regulation arrived decades too late? For the families who lost loved ones in early explosions, no reform could undo the past. Entire communities bore the scars of disasters that might have been prevented. The late arrival of oversight was a reminder that progress often follows tragedy, and that the cost of industrial advancement had already been paid by those who worked closest to the fire. Even after regulations reshaped the industry, the core danger inside every boiler remained the same. Steam did not change. The physics of pressure, heat, and phase transition continued to operate with the same unforgiving logic that had torn apart riverboats and mills a century earlier. Modern engineering strengthened vessels, improved controls, and added layers of protection, yet the fundamental force trapped inside those steel shells carried the same potential for destruction. It remained a power that demanded respect from anyone who worked near it. By the early 20th century, newer boilers used stronger steels and welded seams that eliminated many of the weaknesses found in riveted designs. Better metallurgy reduced internal impurities, and more precise manufacturing techniques ensured uniform plate thickness. Yet these improvements did not erase the risks. Boilers now operated at higher pressures and temperatures than their predecessors. The energy they contained was greater, and the consequences of a failure could be just as severe. With advancement came new forms of vulnerability, some hidden within the complexity of modern systems. Automatic controls helped stabilize pressure, but they also created a reliance on technology that could mask subtle mechanical problems. A malfunctioning sensor or a sticking valve could allow conditions to drift into unsafe territory without immediate detection. When early boilers failed, the signs were physical, rooted in the behavior of iron and flame. Modern systems introduced electronic components that aged in different ways, sometimes failing quietly before their mechanical counterparts showed any strain. Water chemistry remained a critical factor. Modern boilers required carefully treated feed water to prevent corrosion, scaling, and the buildup of deposits that could compromise heat transfer. Even with advanced purification systems, small deviations in chemical balance could set in motion slow forms of deterioration. A microscopic flaw in a weld, a thin layer of scale on a tube, or a pocket of oxygen trapped within the system could create weak points that expanded over time. The vulnerabilities were no longer as obvious as rusted plates or failing rivets, but they were present nonetheless. Inspections improved dramatically, and modern technicians relied on ultrasonic testing, radiography, and pressure assessments to detect internal flaws. These tools allowed engineers to see what earlier generations could not. Even so, no inspection method was perfect. Some defects remained invisible until they grew large enough to threaten the integrity of the vessel. The same unpredictability that haunted 19th century operators still lingered at the edges of modern practice. Engineers recognized that a boiler, no matter how carefully maintained, was always in the process of being stressed by the forces it contained. There were reminders of this reality scattered throughout industrial history. Mid-20th century power plants suffered tube ruptures that released steam jets capable of cutting through metal. Marine engines experienced failures that flooded engine rooms with scalding vapor. Even in well-regulated environments, accidents occurred when a single component failed in just the wrong way at just the wrong time. These events served as a sobering reminder that the balance inside a boiler was always delicate, always shifting. Today, boilers remain essential to power generation, manufacturing, and transportation. Their designs are safer, their oversight stronger, and their materials far more advanced. Yet the principle that drove every explosion in the age of steam still applies. Whenever water is confined, heated, and pressurized, the potential for sudden release exists. Modern systems have reduced that risk, but they have not eliminated it. Behind every gauge and control panel lies the same force that once tore whole buildings apart. Steam granted the world immense progress, but it never surrendered its capacity for destruction. The physics that shaped the earliest tragedies still waits quietly inside every modern boiler, unchanged and patient, demanding respect from anyone who stands close to its power.